Alright, in the previous video we were looking at what the frequency numbers would have to be for the table to show independence or lack of association. And we did the column frequency times the marginal percent for the row to get the number here, the expected number of people in that cell if the table had no association. So we were thinking of it this way, we computed it this way. If we had done it for rows, row conditionals instead of column conditionals, you just switch the word column and row here. And either way you do it, you end up with column frequency times row frequency divided by the grand total. Another way of thinking about it that we'll mention later is to think about it as a marginal percent here from the columns times another marginal percent for the columns. But that just gives you a percent, and then to say, well, how many people out of my overall sample, you just multiply by the grand total. You can see using algebra, one of these grand totals will cancel with that one and leave us with this formula. So we can compute that table of expected frequencies assuming independence by doing column frequency times row frequency over grand total. And when we talked about independence way back in the probability chapter, we said two events are independent by definition when the product of their probabilities is the probability that both events happen, which is a lot like this, and we'll come back to that later. So here was our observed data, and what's our table of expected data, expected assuming independence. So try to fill in a formula here that uses the row and column totals. That's good practice. So maybe go recreate this table for yourself in Excel and create a new table like that. Ready? 3, 2, 1, pause and go. Okay, welcome back from pause. So we do the subtotal here, and I'm going to lock the row on that, times the subtotal here. So I'm doing this in the first row and column of this table, so I'm using the first column here and the first row there. I'm going to lock the column on that and divide by the grand total, and I'm going to paste that. I'm pasting formulas here just so I don't accidentally include all the outlines of the table. One interesting thing to note, what do you think these numbers add up to? What should they add up to? Well, let's take a look. So I'll take their sum, and it's the same as we had there. So we can do that here and here. We'll take the row sums, and they match as well. So that's good. We're saying here's the numbers we would expect to get upon repeated samplings, each at size 31, and we're not losing or gaining any people. So looking at these tables, do these numbers look so far away from these numbers that you wouldn't believe that these came from a random sample from a truly independent population? So think about that. So can we come up with a way to say how far is this table from that table? Well, the first thing most people think of is, well, let's take the difference of this one and that one. So let's do observed minus expected, and do that for all the cells, and then we'll take the row sums, let's take the column sums, and it turns out that column sums to 0 and that column sums to 0 and the rows sum to 0 too. You can probably just see that even without summing. So this turns out to be too boring of a solution. The answer is just always 0 because we're essentially subtracting 31 minus 31 in little pieces. So that first idea doesn't work out too well. It's just too boring. Now most people say, well, let's keep the minuses from canceling the pluses. Maybe take the sum of the absolute value of observed minus expected. That can work, but it ends up too complicated for other reasons. Another way to think of it is if we're expecting, if this is an expected value, that's like a mean, and this is like a data value. When we were doing z-scores, we did observed minus expected divided by the standard deviation of whatever we're working with. turns out for theoretical reasons that the standard deviation of the cells here, if the true population has independence, is just the square root of these expected values. So you might say, let's compute observed minus expected divided by the square root of expected for each cell in the table. And that's not a bad idea, but again, you get the negatives canceling the positives. So what we end up doing is observed minus expected divided by square root of expected, and then we square all of that, and add it all up. So that gives us a formula called the chi-squared value, and here's the big formula for it. Observed minus expected squared over expected. You can see we've distributed this squared over the square root to cancel it. So that is called chi-squared, and chi is written like an x here. And then in the next video we'll go apply that to the table that we've been working on.